Our first speaker today is Michael Anderson. He works for the Department of Water Resources and is currently serving as the climatologist for the state of California. He came to DWR after extensive graduate and postgraduate work at UC Davis in the area of hydroclimate systems modeling and monitoring. Help me welcome Dr. Michael Anderson.
All right, so this talk's actually three. I did 3 for 1 today. First talk will be climate and expectations for change. Then we'll shift gears and talk a little bit about the Central Valley Flood Protection Plan. And then finally close out with a quick and brief look at Arc Storm, which is a USGS hazards study. All right, starting with climate, nothing like looking at a bunch of dots on the screen. And what we have here is this is for Placer County, and you have minimum temperature versus annual precip going from 1895 to 2011. And you start with the little diamonds, and those are 1895 to 1930. And you'll notice they're all kind of on the left-hand side there. Where annual average minimum temperatures, this is taking an average of every day's minimum temperature for the year, averaged for the whole county. And how this is done with the West Map data is they use a prism grid and tweak the prism surface to line up with the gauge data that they had during that time period. So there you have 1895 to 1930, then we have 1931 to 1960, and those are the little squares. And as you can see, they kind of spread out all over the place at a real interesting time. Things tighten up a bit, but as you see as we're moving across and finally end up with the circles, you'll notice the circles are on the other end side of the plot from the diamonds. Showing that 100 years later, we're hanging out in a much different place than we were 100 years ago in terms of our minimum temperatures. Maximum temperatures, you get a little different look at things, and you'll notice that in the really, really wet years, you tend to have cooler temperatures. Well, in Placer County, when it's really, really wet, we have a really good snowpack sitting in the upper part of the county. It tends to keep the maximum temperatures down for the year. Now you'll notice in the really, really dry years, it gets really warm. So this is what's happened. This has nothing to do with projected change. This is what's already in the books. And we're already seeing movement. All right, so a little bit on some metrics we use in the department to kind of look at how we keep track of our water years. And this is the Northern Sierra 8 Station Index, and it's an average of 8 stations listed there on the bottom right. And you see on the map the little triangle showing where the stations are. And the southernmost one is these are the American River watershed. So you see very strong signal of winter precip, summer dryness. The Mediterranean climate, cool, wet winters, warm, dry summers. In fact, December, January, and February account for half the annual precip. So you have 90 days, and on average, that's when you get half your precip. 80% is October to April. How does that translate? This is again for the whole Sacramento River Basin. But you see a very broad hydrograph that actually extends. There's one here. We had the peak of the rainfall was over here, but we see this nice broad hydrograph. And this is where the snowmelt kicks in and extends this hydrograph. But as you can see here, the blue bars are the first half of the century, and the red bars are the second half of the 20th century. And you'll notice the winter flows are picking up, and the spring flows are going down. So again, this is stuff that's already in the books, and this only goes to 2007. So this is already 6 years out of date. After this plot. and see how these numbers change if they do even further. But what we're seeing is less spring runoff, more winter runoff. So you're already seeing that condensing of the hydrograph that has already happened. Alrighty, April 1 is our traditional peak of the snowpack. This is where we let snowpack build until April 1, and it starts to melt out. And these are the percent of average statewide. And you can see in the past we had these really, really monster years. 2011, where everyone's going, I can't believe we've never seen that much snow. It's only down there at 171%. And 1998, 182% of average. So you see, big years now don't look like the big years they used to be for April 1 snowpack. Remember, this is just this point in time in April 1. But we see with snowpack as it evolves over the water year. Here's April 1. At the beginning of like 82, 83, it said, end of the snow year? I don't think so. We're going to build on up into May before melting off. In a dry year like 76, 77, you kind of say, what snowpack? And for those of you wondering about this year, particularly in the south, it was just like that. All right, so year to year, you always think California's different. Here's proof. This is the standard deviation of our annual precip divided by the mean. Puts everybody on the same field. It's the same dimensionless parameter. And we see everywhere east of the Mississippi, one year does look like the next. And for those of you who do flood frequency and follow the Bolton 17B, the independent identically distributed annual flood peaks, for those folks back there, yeah, that works. And they see no reason to change. But look at us out here, and you see in the Midwest and then out here, it's an entirely different story. And we live already in a more variable climate than anywhere else in the continental U.S. And you hear the phrase, more variable climate. You can see back here, that would get people antsy. Here, we're like, well, you're just all going to live our world here pretty soon. Now here's, again, I said 90 days to get half your precip. Well, this is another plot. Previous plot was by Mike Dettinger, this one by Mike as well. And this shows the number of days to get half the total precip. This is average from 1951 to 2008, and you can look and see. And there's a lot of pink dots in California in the southeast desert. So that's because one storm can be their water year precip. But even look on the north coast where you're getting over 100 inches of rain a year, and half of that comes in 3 weeks. So not only do we have our precip condensed into a winter season, we get it delivered in large shots. And that's something we'll talk about as we move forward. Here's a way to look at it, and you're going to keep this notion in mind because we'll talk about this once we circle back to arc storm. But working with Mike Dettinger, developing this precip categorization, and in this case we're looking at more than 12 inches in 3 days, and he said, well, let's compare how we sit with the rest of the U.S. And here's the hurricane world, where they talk about their monster storms. Look at the counts of 12 inches in 3 days. Yeah, nice try, guys. Talk to us when you catch up to us. Anyway, so here's what it looks like for an annual maximum flood peak. And you can look there and you can say some years you can't call that a flood peak. But others you say, wow, that is really something. This is both American and Feather River. And you can see that, right around 1950, you had this set of data to work with, real Folsom. And you say to yourself, all right, we got 50 years of record. And, Bolton 17B says, hey, if you get 30, you're doing good. So we got 50, we're fantastic. It's built, then lo and behold, 1955 comes along. Largest flood that ever, look at it, largest flood that ever seen. Holy smokes, wow, well, we survived that. 9 years later, guess what? There's something even bigger. And then bigger and bigger. So this has definitely brought attention to the notion that, okay, if things are supposed to get bigger and better, and again, we're already seeing bigger and better, and this was enough to motivate a change in the structure of Folsom Spillway, because the way they designed it, we realized it doesn't work. And that notion of it doesn't work is going to continue. So here we need to talk about, we get things in big buckets. And this is a slide from Marty Rolfe at NOAA's Earth Systems Research Lab. And this talks about atmospheric rivers. And atmospheric river events are a combination of a winter storm that draws in tropical moisture. And it's that convergence of warm, low-level, wet air being driven by a strong wind, and it runs into California's topography. And that combination of three things, boom, lots of rain. And what Marty's trying to say is, note that the major impacts of this event in 2008 are more than 500 miles from the low pressure system. The low pressure system was up here in the Straits of Juan de Fuca. Down here in California, we're dealing with 32-foot waves, 7 to 13 inches of rain on the coast, and 6 to 10 feet of snow in the Sierra. This is how we get water. And while it's a little different than a hurricane, nice, compact, everything dropped up, all six there, it's easy to describe. This is a little harder for people to get their heads around because you've got a lot of moving pieces that come together. And here's the moisture source. Now note, very narrow, very long. Here's Hawaii, and this thing extends down past Hawaii. And that is a coherent source of moisture more than an inch. And most of this moisture is in the first 5,000 feet of the atmosphere. Now I was traveling along here, ocean, ocean, ocean. When it gets to California, first 5,000 feet, there's something in the way. And when water air is lifted, it can't hold that water, so it's going to drop it. In this case, in this event, you had 10 inches of rain hitting California. Now, in this study, they were actually looking at North America. That's why you have North Coast is actually up here into British Columbia, and the South Coast is actually California. But then this makes it real fun because we're dealing with the tropics feeding our moisture source. It's not just a storm. You have all the tropical activity going on that play a role in how big our storm is. You have conditions of El Nino, the southern oscillation. You have ripples in the intertropical convergence zone that if they bubble up at the right time that you have one of these excited, you suddenly have a lot bigger tap of moisture to work with. You have the Madden-Julian oscillation, which is this continental size. So think the convection the size of Australia that moves across the tropics. Now it works from the Indian Ocean towards the international date line. And there's a point when it starts in the Indian Ocean and where it gets right here into the maritime continent. For the energy from that much convection, you can imagine that's rippling the atmosphere a little bit. And those ripples actually impact California's weather. And if you line all these things up, it's like rolling 5 5s and boom, there it is. Alrighty, so that's our baseline. That's what we live with now. And here's our expectations that we're going to say. Well, we're going to warm up the atmosphere. Warmer atmospheres hold more water. In terms of total annual precip, it may increase or decrease. There's really not a strong signal there. Hard to find a signal when you're already living with variability that extends from, in the northern, the 8 station index. Our low is 17 inches and our high is almost 90. With that much variability, it's hard to pick out a trend. We do warmer temperatures, we're going to have less snowpack, it's going to melt earlier. The watersheds are going to change. That's going to change our timing and amount of our river flows, and at the bottom of the watershed, we're going to have sea level rise. This will demand a change in how we operate our water resource systems. We've already seen that. But what it comes down to in California, you have to know your watershed. 4 watersheds shown here, all 4 are very different. They all behave in their own way. And while we can make some generalizations, the devil's always in the details, and the details come down to the watershed level. Alrighty, so what do we track? Well, temperature, precip, snowpack, annual and seasonal runoff, our peak river flows, the amount and the timing of them, and mean sea levels. What you need to know for yourself is what matters, when, and why. Not too tall a task. Now let's dig into some of the questions. Well, how will an atmospheric winter storm characteristics change in a warmer atmosphere? How will the ocean temperature and circulation patterns impact our storm tracks, our storm number, the size, and the intensity? How will temperature impacts change the land surface, watershed, the water balance within the watershed? And are we observing what we should be for tracking the change and its potential impacts? Alrighty, well here's one step we're going in that direction. This is something that we're just coming online now. In the past 5 years we've been working with Noah's Earth Systems Research Lab and Scripps Institute for Oceanography to put in some cutting edge monitoring for California. We have these 4 posts. The first one here in Bodega Bay is operational as of last month. And they're called atmospheric river observatories. And we use a wind profiler and a little pink dot called a GPS MET. So the GPS MET will tell us how much water vapor is in the air above us. Wind profiler tells us the wind structure. We actually now will show what the atmospheric river is doing when it's coming on shore. If you think back to those plots I showed you with atmospheric river, you had pretty colors in the water. Get to land, everything goes black. And that's because with the satellites, it only works when water's your lower boundary condition. Well now, we could turn on the image for California with all those pink dots because those tell us how much water vapor is over those points. And we leverage this activity with the Plate Boundary Observatory, who's trying to keep track of our land surface, because for them, knowing how much water vapor gives them a better signal. They can sharpen that up. So they provide the GPS station, we provide the meteorology equipment, we work together, and we both get good data. The blue squares are called snow level radar, and this is a radar, instead of circling out, it shoots straight up. And during a storm, it can tell you where rain is turning to snow. This is a key parameter for figuring out how much runoff is going to happen out of the Sierra Nevada. And as you can see, we have a picket fence now that looks and shows what's happening for California. Now the really neat thing about this is we're working with the California Nevada River Forecast Center. So they can ingest this data, and this initializes their models and improves their forecasting ability. But what they've also done is they realized they can actually pull this metric out of the forecast models, and they can actually publish an estimate of a freezing elevation out 5 days from the numerical models, the atmospheric prediction models, and they actually publish that now on their forecast page. And then all the little circles and dots you see are different soil moisture monitoring. We have a lot of different people who are really interested in knowing that. In the past, we knew it took a while before the watersheds respond. We go 5 months without rain. The watersheds dry out, takes a while for them to wet up. And we usually wait, and we'll see when the river kicks up, and then we'll know, okay, the watershed's wet now. This we can actually track that, and this will help not only for flood forecasting, but this will help with water supply forecasting, because you can tell now if a snowpack's building on a dry watershed, you're not going to see the runoff right away. You're going to pay the watershed for the deficit before you see the runoff start showing up in the rivers. Alrighty, so adaptation, that's the story now with climate change. Where, when, and how am I vulnerable? That's the first question you have to ask. Why should you care about climate change? But what exactly should you care about? How does it impact you? How does the level and timing of your vulnerability intersect with your land use activities and infrastructure? In our case, we have a very defined flood season. And we have a snowmelt season that provides us our water supply that gets us through a long, dry summer. How will climate change impact water resources in my location? There are different thresholds and consequences. Size of your reservoir, size of your population you're serving. Size of the watershed behind it. Think of Frank Dam. Frank Dam has about 500,000 acre-feet of capacity. It's got a huge watershed behind it. So it's not that they fill up the reservoir and then drain it slowly to deliver water into that part of the San Joaquin Basin. They are actively working that reservoir and managing that water through it as a way station until they can get that water moved to where they want it. Much more dynamically than, say, a huge monolith like Shasta, where you can actually catch multiple years worth of water and deliver out and hopefully have some carryover storage. Those give you different problems to work with when you're dealing with looking ahead. And it's good to be able to articulate them with specific thresholds and consequences. And then what action or investment changes the answer to those above questions, and to what extent? Then you can start saying, if I'm going to invest this much money, how much do I get for it? And that brings us to this, because this is a good segue into the Central Valley Flood Protection Plan. So we had an investment of $4.8 billion into improving flood management in California. And part of that You know, it wasn't just, here's a bunch of money, go do something, have some fun. They said, put together a plan. It shows us that you have a way to do this systematically. And the 2012 Flood Protection Plan reflects the state's system-wide investment for flood management improvements in the Central Valley. And what it does is you can look. Now this is really focused, again, in the legislation, they said focus on the part where the state is holding responsibility. And that is a really important point because we don't hold responsibility everywhere. Some places the locals hold that responsibility. And the state has to partner with them. But the areas that you see highlighted in gold, those are the areas that the state has responsibility for. And if you like to scare yourself, you can read all the little bullets there. In terms of billions of dollars of assets at risk in flood protection, that really doesn't measure up to today's standards, let alone what we're going to worry about tomorrow. Alrighty, so we developed a process that figures out, well, how are we going to get our heads around this? And they identified some goals, some management actions, different alternatives they could look at that work across a matrix of water use activities. Because you can't just say, we're doing all this for flood. In California, when you deal with water, you deal with multi-uses. We have multi-purpose reservoirs. We don't have just a reservoir that does one thing. Look at a comparison of approaches, and you know, you can go with the minimal of, let's just bring it back to the 1955 profile. And remember, 1955, that was the biggest flood they'd seen in 50 years, until 9 years later. So, okay, wow, you're saying, well, okay, we'll improve things back to something that's already 50 years out of date. Yeah, okay. Well, let's just focus on the high-risk communities. Then you have some voters saying, excuse me, there's not really a system look there, and you remember the title of the CVFPP slide there, system-wide. And so I said, all right, well, let's go for the gold standard here. Let's enhance the whole flood system capacity, and let's just show you the bill for that one. And look at the policies and guidance on what we're actually allowed to do legally, and then we'll try and piece together the best of everything and come up with what they've titled the State System-Wide Investment Approach. And the idea is to consider the Central Valley flood system as a whole, and you have to understand this from the perspective of what we deal with now, particularly in the San Joaquin Valley. 4 main stem tributaries, 3 different members of the major reservoirs on our reservoirs. 2 are Central Valley Project and the Stanislaus, and the San Joaquin River in front, but Tuolumne and Merced owned by irrigation districts. They are all Section 7 reservoirs. They are all governed in flood space by the Army Corps of Engineers, but each water control manual was built for the tributary. It was not built for the main stem San Joaquin River. So if I can release my objective flow out of each of those 4 reservoirs and I add up all the flows at the bottom of the San Joaquin River at Vernalis, guess what happens? More water is released than fits. So, this is kind of taking a different perspective. Let's look at this thing as a system. Look how we can work together. And again, the focus is on those facilities that the state has an obligation to, that we signed off with the federal government saying that we are responsible for these elements. And we recognize there are fundamental interests of public safety, environmental stewardship, and economic stability. Lots to try and keep track of and balance in making this work. Regional improvements for urban, small communities, and the rural agricultural interests. You're going to have different needs for those different communities, and we have different elements that we can attack system-wide that actually manage the whole system. And you look at the Weir bypass system in the Sacramento River, which is often held up as one of the better flood management ideas. I remember learning about this as a civil engineering student back in Colorado. They held this up and they said, here's somebody who actually did flood management right with this concept. Flood structures, flood storage, and operational changes. Try and put all that together, look at your ecosystem restoration opportunities and try and integrate them in. Policies, guidance, and implementation strategies. It's a nice little sentence that really has a lot of nuances to it. Because land use is not dictated at the state level. We can provide some guidance, but we're built on the notion that the locals have control. And water supply, locals have control. And with the state system-wide approach, the best idea, this is $14 to $17 billion. And to actually lay this out and think, well, how can we do this and work all this out? First estimate says, just the way we do business, that's going to take a couple decades to piece together and work through the process. All right, so we're at 2012. Now, where do we go from here? Well, we're starting with basin-wide studies, actually looking at the basins as a whole and saying, where are our pinch points? Where are our problems? What are our options, again, from a system-wide perspective, and how does that work? And how do you establish system benefits, and how do you evaluate that? Well, then now we have to find a way, again, in the past, flood projects were done locally. How do you bundle those and get people to start thinking in terms of a regional element, the same way we do with our water supply, with our regional water management plans? Bring flood into this so you have more of an integrated water management activity, and do that to build up to make it easier to translate from local to system-wide. And again, we're not doing this by ourselves. We have to work in partnership with our federal sponsor, with the Corps of Engineers, and work at continued improvements. You can't just tell people, wait 25 years and we'll come back to you. We'll be ready to go then. A lot's going to happen in the intervening time period. And so in the next 5 years, which we're already into, we'll have an update to the plan. The Corps will have their Central Valley Flood Management System project, their own system perspective on this, and we'll work together to try and move those forward in a coordinated fashion. Alrighty, so now let's finish off with Arc Storm here. The other big one. Alright, so how many people have heard of the Great Shakeout? No, okay, so one person, all right. So the USGS has a multi-hazard mitigation unit, and these folks are designed to come up with catastrophic events that test emergency preparedness, help you highlight and see, look, when things really go bad, and again, things have to really go bad because emergency response starts locally, and as things are overwhelmed, builds to the state, builds to the federal. Well, the federal's going to get involved, and that's when things go really, really bad. So again, for the feds to be looking at it, these have to be big, bad events. So they started with an earthquake in Southern California. And they did an exercise, and they actually got the public involved and had over 1 million people participating in a what-if scenario of a major earthquake. They had people pretending to be victims and allowed the emergency responders to practice and figure out, oh shoot, we use that road all the time, but now that road is unpassable. And it helped highlight for them some really basic things to tweak to really improve their capacity to provide emergency response services. So USGS said, all right, well, what do we move on to next? And they said, well, let's do floods. And we worked with NOAA Systems Research Lab, and working on atmospheric rivers. And their first, they worked with a group, a design group in Southern California to market things, and their first name for this project was Killstorm. They say, hey, it's going to be bad enough you're going to go tell people, we've come up with this exercise where we flood you out, we're going to make you look really bad, and then we're going to see how we can work together to make things better. Calling it Killstorm is probably not a good way to get the public interested and involved. And so they came up with Arc Storm, and you can think of that both in NOAA's term and in the case of an atmospheric river extreme storm. So this, from Dale Cox, gives their mission. They're looking at ways to minimize life and property, improve quality of life through the USGS, and they do this through the multi-hazardous mitigation unit. And they saw this. This is the legendary flood of 1861, 1862. Flooding over 300 miles in the Central Valley. The Central Valley became an inland sea. Governor Stanford went to his inauguration in a boat and then moved the capital to San Francisco for a while until things dried out. But it wasn't just up here. This was a storm that flooded the whole state. LA Basin was inundated. The San Gabriel and San Diego rivers were flowing so strong across their alluvial fans, they made new channels. Largest community between Los Angeles and New Mexico was erased. And there were was multiple atmospheric rivers, and 12 days separated the flood event in the north versus the flood event in the south. So you had a pattern where you had multiple atmospheric rivers just hammering the state top to bottom. So what they say, well, we want to develop a scenario that's on par with that. A recent paper by Mike Dettinger and a colleague did a paleo study and found out these things show up in the paleo record every couple hundred years. Where Mother Nature gets like I said, the most extreme storm is when all those line up and you roll the dice enough that one time everything comes up right and boom, you win. Only it's maybe not the way you think. So hey, let's take everything we know in modern tools and let's create a plausibly scientifically defensible set of extreme storms that we can plan to. And we can say, what happens if? And so, again, they wanted something they could have a lot of detail to so you could actually plan to it. It's large, but it's not a worst case storm. This is not the probable maximum flood. This was working with atmospheric scientists to say what is plausible. There's a little animation of it. And these are actually an event that happened earlier this year. This is the storms at the end of November, beginning of December. You say to yourself, well, okay, yeah, we did have high water from this, by the way. Interesting thing about these events that you're watching, this is the moisture fields hammering the west coast of the U.S. This is a third of this water year's precip falling in this 10-day period. 3 weeks later, we had another set of storms that dropped half the snowpack this year. Without those two storms, we will be looking at an absolutely miserable water year. Because since January, we are the driest year on record. We blew away 1924 and 1977 by several inches. Alrighty, so with ArcStorm, they just did the very general DEM. They said, okay, let's dump that much water on there, and what do you get? Now what they did, and I should backtrack because I think the missing slide here, this one, looks all nice and pretty and nothing. Go forward again. This is actually how they did it. They took the January 1969 storm, which was a statewide storm. They took the worst day of that and they said, what if the front stalled? And you got an extra 24 hours of that atmospheric river. Now what if that was followed on by our largest persistence event in recent memory? That was 1986, where a series of storms hammered the state and produced a volume of floodwaters in the north that had Folsom Dam really on the verge of saying, we're going to save the structure, goodbye Sacramento, we'll dry out and see what happens. And literally within 30 minutes of that happening. Alrighty, so they piece those two together and here's what happens. Our giant bathtub, the bottom of the bathtub, as you see, it gets quite full in 10 to 20 feet of floodwaters. Zoom in on Sacramento. Alrighty. Now, all people in blue are underwater. Now remember, if you're an emergency responder, if they're going to be underwater, you got to try and move them. Look at all the roads. And this is just to give people that, think about this. And then this brought to light some very interesting. The regional transit said, well, hey, we'll use mass transit to get people out. Oh, snap, we just figured out some of our power stations are going to be some of the first things to go underwater. There goes that plan. Well, there's something that's fairly easy to fix. Raise the power station above the water surface, and it still works. No longer. Alrighty, so $725 billion in damage from an event like this. Yeah, it isn't just $1 billion storm. This would reset the record books. And again, the storm they built wasn't any bigger than what happened in 1861 and 1862. We just got a lot more people and a lot more dollars sitting in the way right now. Demand surge. you know, you're going to erase a lot of things in this event, and it's going to take a lot of work. You saw that happen with Hurricane Katrina. That took out a good chunk of New Orleans. Well, this would be our version of it. To erase that much, it takes a long time to build it back. Little difference between here and New Orleans. This is the 7th largest economy in the world that you're erasing. That's going to cause a little hiccup, more than just locally. Now you look at lifeline damage, business interruption, and this kind of freaked them out because this was 3 times the loss generated by the Great Shakeout. They thought the Great Shakeout was an over-the-top extreme event. And they thought, oh, this number's just got to be off the charts wrong. Well, then in the 2012 Central Flood Protection Plan, we said, well, our estimates were just a quick summary of assets at risk. We showed about $500 billion. And that made them say, oh, shoot, we weren't far off. So don't look at that number and just dismiss it. That is something that is quite possible. It's their bottom line. Top one is a good one for us in the business to kind of chuckle at. Flood protection is not designed for extra. No, we aren't even designed for anything close to that. Even half of it we struggle with. Planning for our arc storm, you know, they're again equating it to their world, but for us, these are helpful because it highlights some simple things that we can do that can improve our ability to respond to any level of disaster. And I'll get to that in a minute to finish off. So they said flood mitigation should consider arc storm. And what it does is, yeah, we can look at these extreme scenarios. And again, they can highlight some really simple mitigation measures that people can take because it highlights those moments of, we think we're going to do it this way, but then we play this through and we realize that you get some of those holes in your plan highlighted for you that you can fix ahead of time. And then you look smart after the fact. And I say Hurricane Katrina is your cautionary tale. There's your object lesson hanging out there for you. And current future research can help to handle an arc storm. Well, what it can help is we can help with forecast and warning. We start to understand how these storms form. We have more time. You have more time to get people out of the way. Now let's talk about that because here we are. Flood management. How do you deal with this? Alrighty, so remember that RCAT thing I showed you where with our RCAT 3s we blow away the hurricane belt. Some historical West Coast Category 3 storms, December 2010, October 2009, November 2006. Okay, there's 3 events since I've been working at the department, which hasn't been very long. We're already there. 97, big flood. 1 quick RCAT 4 episode. Quick is a very important term because with these, it's not only magnitude, it's duration. How long these events hang out. Because had that thing stalled and kept that level of moisture plowing into the watersheds, things would have been a lot worse. 86, 3 consecutive RCAT 4. Like I said, you had a persistence patterns. 3 times, huge volume of water. 83, 1 RCAT 4 storm. We aren't even getting back very far on the historic record here, and you're seeing some really good-sized events. January 69, February 86, those 2 are highlighted because those were the makers that were arc storm. In 4 locations, it was a Category 4 storm. Our 55, again, our design profile event. 2 consecutive RCAT 4 episodes. Here's how arc storm would shake out in terms of this RCAT factor, and you see all along the Sierra. And in this case, you're looking at 2 weeks of this kind of thing. So you're looking at huge volume of water, but what you also see from here is it's not absolutely everywhere. You have places where the topography sticks up in the right way that makes things soggy. And understand this, the same storm approaching from the southwest will cause absolutely phenomenal flooding in the Feather Basin, not so much in the Sacramento Basin. You shift that around so it's coming up from the south, the flooding shifts. In Sacramento above Shasta is going to be hit hard, Feather Basin's not going to be as much. And it all is the shape of the topography versus the wind direction and the moisture being plowed against it. So it's not as simple to say, it's that big storm hanging out on the Pacific. It's how it runs into the state that matters. And one final one from Mike Dinger on the maximum RCATs since 1950. And again, you see major hurricanes that have caused lots of totals. But again, California is right on par there with our extreme events. Now I'll ask you this. Which region is the only region of the U.S. that does not have its own severe storm center? You have the National Hurricane Center in Miami, you have the Severe Storms Lab in Oklahoma, and on the West Coast you have, that's right, you don't have anything. Alrighty, so emergency response, as I said, a low-level event, the local agencies mostly handle it. As it gets bigger, the state comes in, the feds come in. But when we get to those big events, you see it becomes a federal response. And this is important to understand the structure and how this works and how we work together. Because we have to work together. And you have to have those lines of communication ready to go. That was a big hole in the Katrina response. Those lines of communication weren't ready and prepared. And it's really hard to set that up while people are dying on it. Alrighty, so here's how we look at it. With floods, it's not just an event happens and then you get an action. We see these things coming. We have a whole forecast and warning. The idea is to stretch that out to weeks. And you look at forecasting and briefing, coordination, looking at early reservoir operations, pre-positioning, response materials, notifications. The event happens and you have your flood response and then your flood recovery. And the size of the event depends on whether that goes out months or years. We have that in place, we work that, we exercise this. This is something in California we do take very seriously. It'll be major flooding. Our major response is designed to buy time to get people out of the way. We will see this coming, we will know it will be big, and we will know we will be overwhelmed. We aren't going to be surprised by this. But that is not an inconsequential action. And I'll give you this. You saw the level of inundation. Well, consider this. We do not currently have the capacity to house and shelter just the people from the pocket. If we had to evacuate just the pocket neighborhood. There is no place locally to house and shelter for any length of time. They would have to migrate to the Bay Area, which is already overcongested, go over the Sierra to Reno, which, okay, in the middle of an extreme event, that might be a little bit dangerous of a trek. Or they can start working their way to Southern California, again, heavily impacted. That gives you a little bit more pause. It does require a comprehensive and thoughtful evacuation plan for every community. And we have a program in place to build these for every community that they think through. Like I said, we worked with Sacramento. Sacramento worked through theirs and they came to that realization of, oh shoot, our major elements have holes in them and they're working to fix that. Close coordination is the most critical element. Alrighty, so some take-home points here. Atmospheric rivers are a fundamental element of California's water resources. They're at the center of our flood events, but these are also how we get our water supply. Time and location are important, and climate signals like PDO, ENSO, and MGO are important for annual variability. Out here, all years are not the same. Problem is we don't understand how those all work together yet, but we're really working hard to try and figure that out. Climate change impacts has potential for magnitude, timing, and frequency of events. And that happens because you have changes in the land surface, atmosphere, and oceans. That's not an easy nut to crack. A lot to work on. Adaptation starts with the vulnerability assessment. Before you go panicking, take a close look. How am I vulnerable? Where, when, and why? And what investments can I make that can change that? Consequence and timing are important. Can you do phased implementation? You know, if you're worrying about something that's at the end of the century, you've got a little time to get there. Take advantage of that. Central Valley Flood Protection Plan is a roadmap to improve flood management in the Central Valley. It's a roadmap, it's a way forward. But we have to have the will to actually execute that plan and build through it. System-wide perspective, regional focused, local projects. We have a federal partner we have to work through. The federal partner structure is local projects, local sponsor. So you have to work in that window, but we try and take it a little further than it has in the past. I think 20 years, 20 billion, 20 and 20. Arc storm. California's history and future involve catastrophic floods. Not something to panic about, just something to consider. USGS developed Arc Storm to enable planning and response efforts to develop around a statewide extreme event. It's some information and tools to let you evaluate. How do I perform if something like that happens? It's a measuring stick, and it's a good way just to check and see, where do I rate? Flood response starts at the local, extends to the state and federal levels as the event increases in size and scope. For California, evacuations become key for an arc storm-sized event. That will stop. Hopefully it didn't go too long. Thank you.